Welcome to this unit on polydispersity. Before we dive into the topics that are relevant for this unit, let me give you an overview of what you will learn. We will start with a short section on the applications of the DEM of polydispersed granular materials. We will then dive into some fundamental aspects related to polydispersity. For example, how the backing density changes with increasing degree of polydispersity. Also, we will summarize challenges when modeling polydispersed granular materials. In order to be prepared for our quizzes, it is then necessary to introduce some fundamental concepts of size distributions. We will also solve an example related to size distributions, such that you are fit to understand the input of a DEM simulation in this field. Last, we have a short chapter on segregation and computational aspects related to the topic of polydispersity. The prediction of segregation phenomena is an important application area of the DEM. This is why I have included this chapter into this unit. Let us now start with applications. The topic of grinding, or comminution as it is often called, is the first relevant application that I would like to mention. To introduce this topic, I have interviewed an expert in DEM simulations of grinding processes, which is Louisa Orozco from the Netherlands. Louisa, explain to us what DEM can do for us in this application.
Using DEM, you can explore techniques and explore conditions to optimize a given industrial process. For example, I was working for a company that manufactures nuclear fuel, and we needed to grind uranium and plutonium up to a certain particle size. We had these big machines in which you could tune very different parameters, and we ran multiple and different DEM simulations in which each one of them had different combinations of these parameters. This allowed us to map how this combination of parameters would lead to a desired particle size distribution.
Thank you, Louisa, for stressing the importance of size distributions. Certainly, if we grind particles, we will arrive at a particle ensemble with many different sizes. Let us now look at another short video in which we let a granular material slowly flow in a cylinder. We start with a relatively uniform distribution of the small and large particles, and as we let the material flow, smaller particles accumulate more and more near the axis of this wedge-shaped flow region. We call this phenomenon segregation, and this tiny experiment is a simple example for many industrial applications in which this phenomenon occurs. For example, in the field of food and pharma processing, segregation is feared like the devil. The reason is that any non-uniformity in the material, and this is exactly what you see at the end of the video, will have catastrophic consequences for the process. Just think of a tablet that is produced by compressing a powder. If the powder segregates when it flows into our tablet press, game over. And we will have tablets with different concentration of fine and coarse particles, which can mean a different amount of the active substance. Furthermore, the fine particles will not be well dispersed within the tablet. Since the tablet is our final drug product, we might not be able to sell it to a customer due to poor quality, losing a lot of money and waste valuable resources. That is it already for our applications chapter, and we will move on to Fundamentals and challenges associated with polydispersity in DEM simulations. First, let me introduce some wording. We have to remember that so far we have only discussed mono-sized or monodispersed granular materials, meaning that particles have all the same or almost the same size. This is illustrated here on the bottom left. What you see here is a frequency distribution of such a material. On the abscissa, we have the particle size, and on the ordinate, the distribution density QR. Please note that more background on size distributions and on the meaning of Q and R in this plot will be provided very soon. Just be patient. Also, the wording polydisperse will be introduced soon. Next, we need to define a very important term. It is bidisperse, meaning that we have particles that have exactly two different sizes. The first additional parameter to describe such materials is the size ratio. Also, we need to define another parameter that is less obvious. This is the relative amount of each particle. We will later call it a class in such a bidisperse mixture. The corresponding distribution is illustrated on the bottom right. As you can see, not only the sizes may be different, but also the amounts in each class. It is now not difficult to understand what polydisperse means. We may have a plurality of different particle sizes in a mixture, again illustrated here at the bottom right. Excellent! This is a great basis for our next topic. We will look at the packing structure of the particles in a dense granular material. Let us first look at some qualitative information. Here you see the packing structure when considering a bidispersed particle distribution with a size ratio of 8:2. It is obvious that for the two extrema, namely coarse only and fines only, the packing structure is identical and the system is just zoomed. This is the case as long as cohesion does not play a role. If it does, the packing would be different for smaller particles. Specifically, they would pack more loosely. The quantitative data displayed in this figure is the specific volume V, which is simply the inverse of the particle volume fraction phi p. If cohesion would play a role for the small particles, the specific volume would be larger at point B, meaning it would pack less dense, as already mentioned. Interesting is that for mixtures of small and large particles, the volume decreases, meaning that particles pack more dense. The reason for this is that small particles can fill the voids in between large particles, as shown here on the bottom left. Once these voids are filled, which occurs at approximately 30% fines content, the specific volume slowly grows as illustrated in the figure at the bottom right. Let us now shift our attention to a more quantitative description of these effects. On this slide, I would like to summarize the results of a simple two-parameter model for a bidispersed packing published by Chan and Kwan. As you can see, the expression is of moderate complexity and considers the volume fractions delta Q31 of the fines, the packing volume fractions of only coarse and fine particles phi 1 and phi 2, as well as the parameter S, which is simply the small to large size ratio. Note that delta Q32 is the volume fraction of coarse particles, which is simply 1 minus delta Q31. As you can see on the figure on the right, this simple model agrees well with experimental data. Chan and Kwan show more data on this in their publication, as well as a more elaborate 3-parameter model. In the figure on the bottom right, I have plotted for you the effect of the size ratio to highlight its importance. You can see that the densest packings are obtained for the smallest size ratio. This is obviously due to the fact that smaller particles can fill even smaller voids in between larger particles. With increasing size ratio, the density peak drops substantially and almost vanishes at S equal to 0.7. You will see later in our chapter on coupling with computational fluid dynamics that such extreme packing fractions result in very low permeabilities, meaning that fluid flow through the packing is almost impossible. Clearly, accounting for polydispersity is not only important for the packing fraction and bulk density, but also for fluid flow considerations.